Hey guys, where is the last thing that I said? I sort of missed that it closed on us. What was the last thing that I said? Do you remember? Okay. So we'll have, we're studying three different scenarios, right? This is a perfectly inelastic collision, so energy is not conserved before and after the collision, but momentum is, right? So this is case one, right before, snapshot two, right after the collision, and snapshot three, when this pendulum is at its max height h, right? And to relate the height to the initial velocity of the bullet, we'll relate the before and after momentum and the energy, conservation of energy at these 2 points, right? So conservation of energy at 2, and there's no potential energy, there's no gravitational potential energy or other potential energy because it's at its lowest point. So it's all in the kinetic term over here. Okay, and then at the top, the velocity from just know the pendulum, it'll go when it's at the peak. It's all the energy is in its potential energy, and the velocity is 0. V prime is 0 at this point, right? Or I should write V3, right? So, and then this is what we call V prime. So we have this equation. So all we have to do is plug it into each other. So first, let's solve for V. So from this, we have, so we have this situation. Now, V prime is equal to, hold on, guys. All right, let's continue. So we have this. V prime is equal to, related to V by this equation. So for V prime. Now we plug it into here. So let's plug it into this equation. We'll have M plus M, and then M little m squared over this. V squared is equal to small m plus large m and h. Okay, we have this, and then now let's solve for that. So this cancels out with this. We'll bring this over to the, now we'll bring this 1 m plus n to this side. So we'll have small m squared, this. Now we'll just solve for h. And we got an equation for h here. Right. Now, if we want to solve the velocity, now normally we would measure h, so we solve for the velocity, and if we solve for the velocity, this equation becomes m over that square root of 2gh. Right? Now this looks kind of familiar, right? When we did conservation of energy, we have this term 2gh, and we just multiply it by this ratio, right? So that's how we do a problem with inelastic collisions. Now, when we extend this to collisions of 2 and 3 dimensions, I'm just going to briefly go over it, but it's just basically you have to, it's all that we did. We just have to break it down into its components and apply conservation of momentum to each one. So let's say if we have mass A, it's coming in at some velocity, some momentum in this direction, and it hits mass B over here, and it moves. Then after the collision, mass A goes this way, PA prime, and then mass B goes this way, at PB prime. Right? Now, what we have to do is relate the x component momentum in x and the momentum in the y. So what is the initial momentum in the y and the x? So let's consider x. What's the, so if this mass B is stationary, VB is equal to 0, well, we have its initial momentum, right, in the x direction is equal to the final momentums, VB prime times, and then we have to do the components, right? So in the x direction, this is x and this is y. That means that this would be cosine theta prime b plus PA cosine theta prime a, right? And that's what happens in the x. And it's completely in the x, right? I mean, the initial momentum is completely in the x. So this x, the momentum in the x, gets transferred to both particles, or both balls, we should say. And in the y, what is the initial momentum in the y? Well, it's 0. So the total momentum in the y direction has to stay 0. So this means that PB sine y plus PB, I'm sorry, PA sine prime, this is equal to 0, right? So if these two masses are equal, right, what can you say about these angles? Anybody? So based on this equation, what can you say about these two angles if these masses are equal? the momentum in the y direction, right? Well, for this to be, so if oh, I'm sorry. Then what this implies, actually, if these two masses are equal, this implies that these two angles have to be equal as well. Or we should say that the momentum component in both directions have to be equal as well. So if that implies that these two angles are equal. So when you shoot pool, the cue ball and the ball in question are equal to each other. So if you want the ball to go at one angle, you know where the cue ball is going to go, right? You know the angle that the cue ball is going to go in, and it's going to go in this direction, right? So and then you could calculate, you could use this equation to calculate the velocities in the momentum in the x direction, right? So if these two angles are the same, right? These two angles are the same and the masses are the same and this momentum, that implies that the velocities are the same, right? So then these two will part ways at the same angle with the same velocity, right? Okay. Now I want to introduce, before we finish, I want to introduce a new concept, right? I don't want to go into, I don't want to spend too much time in it, given this summer course and there's a lot of more material to cover, but it's center of mass. So what we've been considering the entire time is idealized objects, where we just consider these symmetric objects and we only consider translational motion of these objects, right? We don't consider how these objects can rotate, right? We haven't studied what's inside of these objects, right? And what we assumed here was that if we averaged the mass of all the positions of these points, they would average down into a single point. And we could represent the motion of that object by the motion of that single point. And that single point is called the center of mass. And this is important now as we move into rotational motion. So the center of mass of an so let's consider two balls, right? Let's say we consider these two balls as one system, right? If we were to replace these two balls with one ball, where would that ball sit? Right? And it would sit we want to find the average position where that mass would, the combination of these two masses would sit. And the way we do that is by measuring this distance, XA, and then we have XB, right? And the way we find this position, X center of mass, this is the center, where the center, where these two objects would sit, right? The center of mass, all right? This position would be just the weighted average of the two positions. And it's weighted by the mass. So if MA is more massive than MB, this center of mass would be closer to MA. It's weighted by how much mass is there. And by me saying weighted, I mean that in terms of statistical analysis, where one quantity means more than the other. But this is where the term weighted actually comes from, right? If this has more mass, it weighs more, so this side would count more than this side if we're trying to find the center point for both these masses, right? That's actually where it comes from. So what we do is a weighted average, and we weight it by the mass times the position, right? Divided by the total mass of both objects. Oh, I'm sorry. Yes. We're actually finding the average, the average position for both of these, right? And this is what we mean by center of mass, right? Where can we put both these masses so that if we made one massive object, where would that massive object sit so that these two masses would can be approximated as that one mass if it's moving, right? And this is how we find that, right? It's the mass times the position plus MB. Now, where this comes into play, imagine if we throw an object. Let's say, well, in the book, they throw a wrench, right? Let's say I throw a wrench or this marker, right? How will it spin? If I throw this marker, you know, there's some, not only will it move in a projectile motion, but the object itself will probably have some kind of rotational motion, right? And generally, it will rotate about its center of mass, right? So for this object, because for this wrench, because the head is so much more massive than this length of the handle, the center of mass would actually be somewhere over here. It's not, you know, it's hard to find a center, but it would be somewhere over here, right? And when I throw it, what will happen is that it will spin about that center of mass. And that's where it comes from. And then the center, if we follow the motion of the center of mass, as I'm throwing it, that center of mass will follow the projectile motion. The object itself may move, may rotate around the center of mass and may look like it's moving weirdly. So if we throw the wrench, right, and we just follow this end, it won't look like projectile motion. It'll look, you know, something like this. And then as it rotates to the next point, as it keeps rotating, it would rotate up to here, and it's hard to follow. So we break it down into two motions. You know, the translational motion, of the center of mass and the rotational motion of the object itself. And it's important to say that we deal with these rigid objects, these objects that don't deform. These objects are perfectly rigid. You can't compress them or expand them. And if you look in the book, they show a diver jumping. That's a good example of translational, but that could also be a rotational motion of the object itself. Right. And this is, and in the most general sense, let's say if we have many of these masses, right, then the center of mass would just be the sum of all these positions like this, and we just sum it up accordingly. Right? And this is the total mass. The total mass is just the sum of all these objects. Right? And for, let's say for the wrench, I hope you see where I'm going with this by now, since we've used calculus so much, right? So we break down this whole wrench into small infinitesimally sized pieces, and we sum up all these little pieces, right? We sum up all these little pieces and these positions. And if it's infinitesimally small, it becomes an integral. And here, in the most general sense, the integral will look like this. Right. Oh, well, let me do it in the x direction. So this is in one dimension, right? This point mass is along one line. And then if it's a rigid body that's continuously, you can integrate over the size of that object. Let's say if we had a rod instead, right? Or even the wrench, let's say, we would integrate where the mass is at each point, and we'll have this. One over m x, and we integrate dm. dm would be these little segments, dm. So it's the mass of that little infinitesimally small segment times the volume, or dx. And dm is usually equal to the density. In this case, since it's in one dimension, the line density times dx. Right? Now let's go to 3 dimensions. So you could separate the center mass of each coordinate into and take the average in each dimension separately. And in the most general sense, the center of mass position of an object is equal to this. Now here, dm, what does dm mean? Well, dm is the mass of each infinitesimally small object. And what this usually means is that it's the density of that object times that volume of the size, the volume of that element over here. So it's just the rho times the dimensions, the cubic dimensions of that volume. Here we're dealing with the cubic volume element. Now, normally I would go through some examples. Please look at them at home. it's very, please read 9.8 and 9.9 at home. It'll be important for Thursday's lecture. But I won't have you calculate the center of mass of different objects. We won't do it in this course. It's too intensive and there's more important material to cover. But please read this at home, okay? And any questions? I know this stuff I kind of skimmed over very quickly, and conceptually it's kind of hard to understand. You'll have to think about this for a bit. And then read 9.9. I sort of went over that a little bit. And then we'll start chapter 10 on Thursday. We'll do chapter 10 on Thursday. I'll post the quizzes for 8 and 9 due this weekend. Don't worry about the quizzes for 6 and 7. We won't have quizzes for that because we had the test. So maybe I'll give it for extra credit, but we'll continue. Any questions before we end today? Okay. Take care, guys. I'll see you.